So what does it become? 4 times radical 10 radical 5?
40 radical 5.
Yeah, 40 radical 5. And then what about our last term?
I think it's 25 and 2.
25 times 2 is 50.
50 and 5.
You can't divide this by 50.
What did I?
Oh, 25.
25 and 5, and radical 25 is
5.
5. So we get 5 radical 5. Yes?
Yeah.
Okay. Once we get to this point, 6 radical 2 minus 10 radical 2 plus 40 radical 5 minus 5 radical 5. What do I do now?
Negative 4 radical 2.
Where'd you get that from?
You combine them.
I combine my like terms, and then?
Plus
35
yeah.
radical 5.
Yes, and then I combine my like terms there. That's all. These two, if I've got 6 radical 2's, and then I take 10 of them away, I'm left with negative 4 radical 2's. Similarly, if I've got 40 radical 5's and I subtract 5, I'm left with 35 radical 5's.
Why does it sound like a whole crowd outside?
It is.
Really?
Yes, the lower school, they're all going down to the classroom.
Whoa, is that COVID sick?
Yes. There's small enough numbers. All right, next. Which one? 27. 27.
Excuse me?
M minus y.
What?
No, m over y. M over y minus y over 1 over y minus 1. What am I going to need to do here first? What am I going to need to do first?
You could put a over 1.
Put what over 1?
Y over 1. Or
How's that going to help me?
so when you you need to have a common denominator.
Okay, but 1 is not a common denominator there.
I know, but that's what I did.
How am I going to rewrite that top? The problem is, in order to divide here, I'm going to need to do a keep change flip. Yes?
Yeah.
But I can only do that if I have 2 fractions. The problem is I don't have 2 fractions right now. On the top, I have a fraction and then something else being subtracted from it. And on the bottom, I have the same sort of thing. So I need to combine the top and the bottom. I need to make each of them just a single fraction on top and a single fraction on bottom. How can I combine m over y minus y?
Make the y by itself, the denominator y. So it'll be y squared over y.
Right, so I'm going to rewrite it as m minus y, m over y minus y squared over y. Now I've got like terms on the bottom,
M minus y.
where I've got common denominators. I have m minus y squared over y. Okay, that's on the top of the fraction now.
Then you can do that one.
And the bottom fraction, what am I going to do?
1 over y.
1 over y minus
Y over y.
minus y over y.
And the 2 y's cancel. Later.
No,
Oh,
you're subtracting. When we subtract or add, we keep the common denominator and we just add or subtract across the top.
Oh.
So what do I get? 1 minus y over y. Once I get to this point where I have, notice, I've combined these into a single fraction on top and a single fraction on bottom. Now I can do what?
keep change.
Now I can keep change flip. So I'm going to have what?
M minus y squared over y times y over 1 minus y.
Yes.
Now you can.
And now I can cancel because now I'm multiplying. So the y's cancel out and I end up with
M minus y squared over 1 over y.
over 1 minus y. Yep.
Oh.
There you go. So anytime you have something like this where you've got fractions within fractions, before you do your keep change flip, you need to make sure that you're combining everything into a single fraction on top and a single fraction on bottom. Otherwise, the keep change flip isn't going to work correctly. Especially with that bottom. Remember, we can always convert something like 1 and give it a different denominator. We can rewrite 1 as y over y. Similarly, we can rewrite y as y squared over y. Those are equivalent to each other. And then once we rewrite them like that, then we've got common denominators and we can subtract. Oh! Yay!
If it's nice, do we do it outside?
Sure.
Woohoo!
That'd be fun. I'd like to do that again, like we did in the beginning of the year.
Yeah.
I remember when I was in that class, I saw you guys, I was like, man, I wish I could be in that class.
Well, I would be thrilled to do that again. I really like that when we took tests outside. Yeah, so if the weather's nice on Tuesday, we'll do that. Okay, next. Any other problems? I know somebody needed 30.
Oh
30.
yeah, that was me.
Dude, I finally remembered the
Oh, yeah, what was the
formula for it.
So
It was like
30.
800. It was like 800.
What are they asking for in 30?
Oh, they're asking for.
Dude, they're not.
Volume.
The volume of this cylinder. How do we find the volume of any kind of right solid, whether it's a right cylinder, a right prism, or just a sort of general right solid? How do we find the volume? What's our formula there? You need to know these formulas. Area of base times height. So how am I going to find the area of the base of this? They tell us the height. What's the height?
24
The height is 24 what? Dollars?
centimeters.
24 centimeters. How do I find the area of the base?
Find pi. I mean, not pi, like 6.
What kind of shape is the base?
Circle.
So how do I find the area of the base?
Pi.
Pi r squared. Okay, pi r squared. What's the radius?
6.
So I've got pi 6 squared. What does that become?
36 pi.
36 pi. Now that I've got the area of the base, square centimeters. Now that I've got the area of the base and I've got the height, I can just plug them in. Yes?
Yeah.
Good job.
And what am I going to get? What's 36 pi times 24?
Almost done.
It is 164 pi squared.
It's, what is it?
880 squared.
No.
860.
Thank you. 864
Pi.
pi.
Oh yeah, that's what I was getting, yeah.
Pi what?
Centimeters.
Not centimeters.
Square centimeters.
No.
Cube.
Cubic centimeters. When it's volume, we need cubic units because we're measuring the height, the depth, and the width. We're measuring 3 different dimensions, so we need cubic units.
What about 4 units?
You could, yeah, if you have a 4-dimensional object, you would need cubic, you would need quadratic, no, not quadratic, what would you call that?
Is a bubble a 4-dimensional unit?
No, four-dimensional objects, you can do math with them, but we can't perceive them with our senses because we can only perceive things in 3 dimensions.
It's like a 2-dimensional object trying to perceive a 3-dimensional.
Right, so like, yeah, it'd be like, imagine if you were flat, you know, you live in a world that's totally flat and there's only like left, right, and up, down, there isn't a 3rd dimension. And then imagine like then trying to think about something that goes off of the plane of your existence. That's a 3-dimensional object. And so that's what a 4th dimension would be like. It's sort of debated whether these things actually exist or whether they just sort of exist in a mathematical sense. There are some areas of physics, most notably string theory, which has to do with the very tiniest particles of matter. And some of the math that's proposed for those involves multiple dimensions, like 17 dimensions. You have to have that many dimensions for the math to work on those. So like you've got, you know, so 1 dimension, with 0 dimensions is a point, yes? 1 dimension is a line, or a line segment. 2 dimensions would be a square. So far, on this flat surface, I can depict these. But to depict a 3-dimensional object, I'm going to have to sort of cheat and make it an illusion, because 3 dimensions is coming off of this surface. So if you imagine our world like this flat surface, if you could go at 90 degrees to all the other 3 directions, that would be a 4th dimension.
Whoa, isn't there like a cube that's used to describe the 4th dimension?
So a 4-dimensional cube is called a tesseract.
That's the word. I was thinking about it because I always remember the
Yeah.
name of the
You mean from like a meter?
Yeah. Well, I mean, it's nothing.
That's what a
like that.
tesseract is. So you know how like a square is a 2-dimensional object that's all right angles? It has all the sides the same length. And then a cube is a 3-dimensional object that has all the sides the same length and all right angles. A tesseract would be a 4-dimensional thing that has all the segments the same length and all right angles.
And like, isn't he inside like also like it's weird, right? It's like blue.
No. All right. Anyway, moving on. That's outside the scope of this course. Other questions from the homework that you want to go over? Last call.
No.
Did everybody get numbers 20, 21, and 22 correct? Be here on time and you'll hear them. Because most of your classmates were here for that.
Yeah, x minus 5 times x minus 4, x minus 7 times x minus
Yeah, as long as you rearrange them correctly, you're going to be fine. What about 23? Did everybody get that one correct? This functional notation sometimes throws guys off. You got to make sure you square to the negative 3 first, so it becomes positive 9. Then you multiply by negative 2. It's negative 18 plus negative 9 minus 7.
But the first time I did it,
So it's negative 34.
that's what I got. But I got it right.
Okay, good.
Alright.
Last call about the homework. Okay, lesson 71. Go to page 288. Lesson 71 has two things. They're both slight expansions of things we've done before. First off, we've been factoring trinomials, quadratic trinomials. What does it mean when I say that something is quadratic?
Four
No,
sides.
no. This is a term I expect you to know. You should have it in your notes somewhere. I've written it on the board a couple times at least over the course of the year. You can try looking. Maybe you have some notes. Maybe you want to look through the book somewhere. The answer isn't up there, so looking up there isn't going to help. When I say something is quadratic, we need to be able to talk about these things. We need to make sure we know our terminology. When I say that something's quadratic, what does that mean? When I say an expression or an equation is quadratic? No. It actually doesn't have anything to do with 4.
The word quadratic tells us that the highest power of the variable is 2.
Thank you. The highest power of the variable is 2. What's another way that we have learned to say that? Means that it has a degree of what?
2.
Of 2. As opposed to a linear equation. What's the degree of a linear equation?
1.
The degree of a linear equation is 1. So quadratic equation has a degree of 2. That means it has what?
3.
3 what?
3.
No. Because we're talking about quadratic trinomials. Something can't be quadratic and have a degree of 3.
Oh.
Because quadratic means it has a degree of 2. So it can't have a degree of 2 and a degree of 3. It doesn't work. Does not compute.
It's like a degree term is negative.
Has 3 terms. Trinomial has 3 terms. So something like x squared plus 2x minus 8. What are the factors of this? X squared plus 2x minus 8.
Okay. For both, like,
X is not a factor of this. What are my 2 factors of it?
2 and
They're both going to start with x,
yeah.
but what are they?
Negative 4. No.
Plus 4.
Yeah, positive 4 and negative 2.
X plus 4 and x minus 2. Yes, x plus 4 and x minus 2. Because 4 and negative 2 multiply to give us 8, and they add to give us 2. Okay, we're going to sort of deal with some third degree things, but only sort of. Okay, imagine I give you something like this. X cubed plus 6x squared plus 5x. Say, wait a minute, Mr. Oriani, you said we weren't going to have to deal with third degree equations or expressions.
Yes, so it says x and x.
We don't really. Why? What can we do with this expression? What can we do with it?
Make 1x squared.
What can we do with this? You said something that was along the right lines, but it just wasn't clear what you were saying. What can we do here? We've got x cubed, 6x squared, and 5x. These 3 terms here in this trinomial.
Switch them.
Remove.
I can't just remove an x.
Well, I don't know. Like,
You add an X, but not in a.
We're not adding anything.
Do it like a distributed.
You know how you put like the two x's for first one? Maybe you can put like x squared for one.
What's the name for the operation, for the process that I want to do? You need to know the terminology here. You need to be able to talk clearly about what it is that you're trying to do.
Distributed?
Distributing is close. We're doing the opposite of distributing, though. We're going to not take away.
Redistribute.
I'll give you a hint. It starts with an F.
Factor.
Factor. We're going to factor out what? An x, because notice each of these terms can be what?
Divide by x.
Divided by x. So if I divide x out of each of these terms, what am I going to get? X times what?
X
X times x squared, 6x.
Plus 6x
Plus 5.
plus 5. Okay, yes. When I've got the variable represented in each of the terms, I can divide it out. Notice I could have done this also. I could have had x to the 4th plus 6x cubed plus 5x squared. What could I have done then? What could I have factored out in this case?
Factor about x squared.
Factor out x squared. And what would I get?
X squared
Squared.
plus 6x plus.
Yeah, I get the same thing. Now, once I get to this, I can keep breaking down the factors further because now I notice one of my factors is x, and the other factor is this quadratic trinomial, and I know how to factor those. So how can I factor this quadratic trinomial? So x is still one of my factors here, but I'm going to break down the quadratic trinomial into two other factors. What are the other two factors going to be? No, x is not one of the factors.
Well, we put x.
Oh, you're going to write x at the beginning of each one. Each one's going to start with x, yes?
And then
But what are the two factors?
5 is a constant.
2, 3.
No.
1 and 5. 5.
So, my first factor, so I got x times, what's my first factor?
5
The second factor? No.
plus 5.
What plus 5?
Oh, x plus 5.
Thank you, x plus 5. It's like speaking complete sentences. X times x plus 5 times
Plus 1.
x plus 1. Because x plus 5 and x plus 1 are the factors of this quadratic trinomial. So notice I can do this in two steps. If I see something like this, even though this is a third degree expression, I can factor out an x from each term. That's one of the factors of this expression. Then this is the other factor. And this one I can keep breaking down further. At this point, can I break down any of these anymore? Can I factor anything out of any of these three terms?
No.
No. How can I check my work once I get to this point?
Do the thing.
Do what thing?
X.
Yeah, I can multiply them together, which is going to involve some distribution. So first I could FOIL these guys, and I get x squared plus x plus 5x plus 6x plus 5. And then x is still my other term. So I get x times x squared plus, x plus 5x. X plus 6, x squared plus 6x plus 5. And then I multiply in that x, distribute that, x cubed plus 6x squared plus 5x. Oh look! I got back where I started. I guess I did that correctly. We want to see how far we can break these down. Sometimes we're going to have to divide out a variable first. Take a look at the second example at the top of page 289, example 71.2. Notice there my three terms are 4bx cubed minus 4bx squared minus 80bx. What's my common factor that I can divide out there?
Yes.
Not just bx.
Yes.
Yes, squared.
No, I can't divide bx squared out of the last term. What else can I divide out of each of those? I got 4bx squared minus 4bx cubed minus 4bx squared minus 80bx. 4bx. Notice, in addition to dividing each of those terms by x, I can also divide each one by b, and I can also divide each one by 4. I'm factoring out my greatest common factor. So I divide out 4bx, and then notice they have it written out for you there. I'm going to get 4bx times x squared minus x minus 20. And x squared minus x minus 20, that's a quadratic trinomial that I know how to factor. And I'm going to break it down to x minus 5 and x plus 4. So my final answer is 4bx times x minus 5 times x plus 4. This can also be useful when your first term has a negative sign in front of it. Notice how this process that we use to break down quadratic trinomials assumes that the trinomial starts with just x squared. If it starts with something other than x squared, we're going to have to deal with that first. So with the third example, example 71.3, we have negative x squared plus x plus 20. We need to make sure we only have x squared at the beginning. What can I do to make it x squared from negative x squared? What can I divide out? Not negative x. I can't divide negative x out of 20. I can divide negative 1 out of it. Because negative x means negative 1 times x. So then I get negative 1 times x squared minus x minus 20. Then I'll flip the signs on all the terms. All the terms. Then x squared minus x minus 20. I can apply my normal procedure to that, and I get x minus 5 times x plus 4. So finally, I get negative 1 times x minus 5 times x plus 4. Or negative x minus 5 times x plus 4. Yes? Okay. Questions about these? Okay, the second thing in this chapter is just sort of annoying. This is actually going to come in handy later. Technically, our variables, what kind of things have we used for variables so far? What is a variable, first of all?
A letter.
Okay, but like if I'm reciting the alphabet, are those all variables? I mean, it could be, but
It's like something that you use as a placeholder.
as a placeholder for an unknown quantity.
Okay.
And usually we're going to use
X.
letters, yeah, X or something. So this is, placeholder for an unknown quantity. Remember, what did we say algebra means at the very beginning of the year?
Oh, that's.
Algebra is Arabic for the unknown. A placeholder for an unknown quantity. Normally, up to this point, we've been using things like X, Y, Z, Q. Sometimes we use things like N, capital N, or even WN you can use. Your variable doesn't need to be a single letter. Sometimes it's going to be convenient even to do something a little different. This is particularly useful when we're describing some real-world situation. So for example, say I want to talk about the number of dollars that Tom and Bill have. And in the same problem, I also need to talk about the pineapples that Tom and Bill have. How many different variables am I going to need here? Am I going to need to do this problem? If I need to talk about dollars that Tom has, dollars that Bill has, pineapples that Tom has, and pineapples that Bill has. I'm going to need 4 different variables. So I could just call them X, Y, Z, and Q. I could do that. I could call them
A, B, C, D.
D. I could call them A, B, C, D. Maybe I want to help myself keep track of what these different quantities, variables stand for.
You like T, B, B.
Right. So if I've got dollars that Tom has, here's what I can do. Dollars that Tom has. D subscript T. We write a little t lower. And we can have dollars that Bill has. We write D subscript B. So just by looking at the variables, it helps me keep them straight because I know that D, here I'm using to stand for dollars, and then T or B tells me whose dollars they are. D sub is usually what you say. D sub T means Tom's dollars. D sub B means Bill's dollars. And then for pineapples, what can I write? Tom's and Bill's pineapples. P sub T and P sub B.
Do they have to be capital? What
When
do
you use
know?
when you use subscripted variables, we're pretty much always going to use capital letters. Otherwise, it's just visually it's too confusing. Please don't touch his things. Don't touch his things. He can get it himself. Thank you. So but be careful because D sub B are not the same variable. If you have something like this, 5 D sub T plus 6 D sub B, are these like terms?
No.
No, they're not. These are two different variables. I just named them similar things to help me remember that these are both representing dollars, belong to different people. They're different quantities. They're different variables. They're not like terms. So when they give you a problem like one of these systems of equations, for example, like at the very bottom of 289, notice you've got 5 n sub n plus 10 n sub d equals 125. And your second equation is n sub n plus n sub d is equals 16. How many variables do I have in this system of equations? 2. The first one is n sub n, and the second one is n sub d. Those are my two different variables. Instead of using x and y or p and q or a and b, I'm using n sub n and n sub d. Right now, it's just annoying because you have to write more. But this actually does come in handy later when we're doing, especially next year, when you do time distance problems. I guess we do a bit of those this year. Time distance problems where you have two different people traveling for different lengths of time at different speeds. So you've got, the time of your first person. You can use numbers for the subscripts, by the way. You got T sub 1 and T sub 2. That's the time the second person travels for. And we can have V maybe for velocity of the first person and velocity of the second person. And so then this will be really useful when you're setting up your equations to make sure you set them up correctly. Right now, it's just kind of an annoying thing where you have to write a little extra, but get used to seeing variables that look like this also. I could just as easily have used PQRS for these, but I'm going to choose not to because if I use these, if I'm talking about two different people's times and velocities, this is going to be much easier for me and for anyone who's looking at my work to keep track of what's going on. This is much easier to understand because it's dealing with a real-world scenario. The math will be the same if you use ABCD, but we want to make sure that our math is accurately describing what's happening in the real world. Yes?
Yes.
Okay, when you get to physics, alternative variables like these are used all the time. Anyway, sometimes even Greek letters are used as variables.
Oh yeah.
Do we do that?
So like you might have, like this, delta y sub y over delta sub x.
Yo.
You might have something that looks like that. And these are two variables here. All right, that's all I've got. Homework tonight. The following from 71.
Should we do 71.5?
71.5. Yeah, let me tell what the homework is, and then we'll do that one together.
Alright.
Homework is following from problem set 71. Hold on, let me make sure that this makes sense.
Wait, isn't 71.5 just a normal relatively any kinds of problems?
Say that again? Yeah, 71.5 is just like any other elimination problem. We're just using subscripted variables.
It's not.
Shh, please be quiet.
Oh my goodness, bro.
Okay, please skip the following for 71. You're going to skip the following. On to 71. Skip 1 through 7, 23, 25, and 29. Corrections are due today, please, by the end of the day, and test on Tuesday. Goodbye.
Can I go to the bathroom?
Yes, you may. Hey, you want to do